This is a sine wave. Considering you spent the last school year dealing with these, you've probably come to know and hate this shape, and for good reason. Trigonometry is awful, and the number one thing I'm glad about post-AP test is that I'm never doing it again. However, the sine wave itself is actually vital to how we hear sound, especially in music. If you play a pure tone like this one, you're actually playing a sine wave. What the speaker is doing is just moving back and forth in the sine pattern, or oscillating, and doing so creates pressure variations in the air, sort of like ripples, which follow the same pattern. Then, our ears can ever so graciously detect it and we hear a pretty boring sound. Now, playing sine waves and chords or whatever can sound pleasant. But there's a lot more to music than just that. We need drums, pianos, voices, synths, whatever it may be. Surely it would be impossible to create all the distinct and interesting kinds of music we hear today with nothing more than only sine waves, right? Wrong. Truth is, every sound you have ever heard is made up of sine waves. So what does that actually mean, that everything is made up of sine waves? Well, basically what's happening is that any given sound is made up of an infinite series of sine waves increasing in pitch, called the harmonic series. A good way to demonstrate this is by using the first few and playing them by themselves, then together. As you can hear, the pitch of each subsequent harmonic is a bit higher than the last, but they get closer and closer. If we pitched our sound down to 1 Hz, meaning that this overall shape contained within the box repeats once a second, the first harmonic would be 1 Hz. The second harmonic would be 2 Hz, the third harmonic would be 3 Hz, and so on. While this is a linear progression, the notes seem closer together because the second harmonic is twice the pitch of the first harmonic, while something like the 100th harmonic has a 100:99 ratio of pitch with the previous harmonic, making them seem really close. Also, the harmonics decrease in volume, because if you had these absurdly high notes all playing at max volume, it'd be a really terrible sound. So, let's start putting some harmonics together and create some sounds. If we first add a few harmonics, you can still sort of hear them individually. At some point though, especially if we move the note around, our brain sort of starts to just fill in replaced with a single sound. So, if we add the first 30 harmonics together as a single sound with a decreasing volume, we get this. Notice how the waveform of that sound is shifting from that sine waveform to more of a linear and diagonal line downwards. We can then extend this out to an approximation that includes the first 256 harmonics, and we get this. Not only does it sound clear, but look at that waveform. It's definitely approaching that repeating diagonal line, and if we were to extend out to infinity, we would have an exact approximation of that waveform, which is called a saw wave. The equation for this harmonic approximation can be represented as a series, or an infinite sum of sine waves, with this expression. In these kinds of series, n simply means the term of the series, so 1 on the first term, 2 on the second term, etc. When you write the series out, it'll look something like this, with each term being a harmonic. So, in order to measure how it approaches the saw function, we can graph the saw function using this equation. Then, we set gx to be our sine wave series written out for different numbers of harmonics. This example includes the first 3. We can then find the difference between fx and gx using the formula for average value. Since these functions are both symmetrical over the x-axis, the absolute value must be taken or else we would just get 0. From there, we just calculate this out with different numbers of harmonics included in our series, starting at 1 and going to 20 since it would take a long time to do more. When we do that, we get this table, with the x value being the number of harmonics and the y value being the average difference. Also, I'd just like to note that I discovered Desmos's Braille mode while working on these functions, and I still can't quite think of a reason that exists. Anyway, it's now time for our favorite activity ever, finding the line of best fit. This took me a while because I couldn't figure out what kind of function it was actually following, and to be honest, that's probably some really goofy and specific function, but I was able to get this. So, our lovely function is 0.456363 over the 3.84726th root of x. Since we know that any nth root of x does approach infinity, we can say for certain that this monstrosity of a function does approach 0, meaning that with an infinite number of sine waves, we can perfectly recreate a saw wave. Thank the Lord. Anyway, up until now, we've just looked at recreating a saw wave, but honestly, the saw wave sounds really harsh and I don't quite like it. What else can we do? Well, there's the square wave, which uses the same series but only employs the odd-numbered harmonics. The triangle wave also only uses odd-numbered harmonics, but the volume of the harmonics decreases quicker, giving it a softer sound, and every other harmonic is out of phase by 50%, which means that it's starting those harmonic sounds halfway through the sine wave. How about recreating other sounds, though, instead of just specific waves? That is also possible, but the approximations in this software are rough due to only having access to 256 harmonics. To get slightly better approximations, we can use another software which allows us to essentially move harmonics around and change the sound over time like we would in real life. Still, there are only 512 harmonics, so the approximations are better, but not fantastic. Either way, using this, we can recreate sounds such as this one. Since it's a longer sound and the original sample is pretty low quality, it's kinda weird, but it's close enough that you can tell what it is, at least. Another interesting thing you can do is approximate some instruments and make a beat. All that can be done just by approximating sounds with anywhere between 64 and 512 harmonics out of an infinite series. So, next time you find yourself beefing with sine waves, just remember that the song you've been binging, the dialogue in that show you're watching, or even the words that I'm speaking right now are all made of them.